are compounds aromatic? That kind of fun thing. At the very end of chapter 18, you'll get some reactions. For the most part, all of those are really going to do is talk about some kind of additional chemistry of aromatic compounds, in particular a phrase known as benzylic compounds. We might as well go ahead and start with benzylic, because it also showed up on the quiz, which, by the way, I will give you points back for that question. Okay. What does benzylic refer to?
Benzene.
You would think benzene makes sense, except benzene refers to the specific compound that is C6H6. If you look through that exam, benzyl is not referring to benzene. It's referring to something else.
Something's benzylic, is it a compound with that on it, or is it a non-double bonded?
Benzyl, spelled B-E-N-Z-Y-L, is a substituent. Okay, the YL should be your clue that you're looking at a substituent on a larger section. What is that substituent? We could say, oh, it's a benzene ring. Of course, it can't be benzene because benzene is just C6H6, but it's still not benzene. And so what you started to do was addressed as something extra. So you've got the substituent part. It's actually referring to one more addition. Okay, benzyl. I'm going to have to just do a whiteboard on this. So we've got benzene.
Is that a substituent on an ether?
No, but not a bad guess coming from the exam. We've got benzene. We have this case where this is now our substituent. All right, what is this one referred to? So this is our substituent. Anybody know what that substituent is called?
Toluene.
Toluene would be another thing like benzene if it was not a substituent. Okay, toluene refers specifically to this compound. Okay, so now in this case, was it C7H8? 9? 8. I think it's C7H8. Okay. The one with the brackets that I'm labeling as substituent right now does not include this extra carbon. Okay, the brackets are going through the bond. So it's just referring to that ring now being attached to something else. Okay, that substituent is referred to as a phenyl. How do we know it's a substituent? Again, with the YL ending. Okay, so the next one is what's going on with benzyl with our YL. Well, as you guys have all been guessing, the benz does mean we've got a ring, but now the substituent, come on, is this piece. What's the big difference? Which I didn't draw super well.
It includes an extra carbon.
It includes the extra carbon. Okay, that position is known as, where you were going, benzylic. Okay, it is the position immediately next to a benzene ring. The chemistry of that position is really different. Because it's different, we pick up this new substituent name. That's where we get benzyl from. Okay, very much the same as allylic. You guys remember allylic? What did allylic mean? It's the carbon next to a double bond. Okay, the chemistry of that position changed drastically due to resonance. What's going to happen with our benzyl? Same thing. Okay, if we went through and tried to highlight, let's go through in blue, what we have here is effectively an allylic position. an allylic position that is then further substituted with the rest of that benzene ring. Okay, so the chemistry between allylic and benzylic are very, very similar as far as that extra carbon goes. Okay, so when you see benzyl with the YL, that's what we're referring to as a substituent. Okay? So back to what we're looking at in Chapter 18. They're going to look at aromatic compounds. So it's primarily kind of the background information, the nomenclature, what makes a compound aromatic, why we can call things aromatic. So there are a lot of different cases where they can show up. You've got benzene, toluene, common solvents. In the old days, you can talk to some older organic chemists, and they would wash their hands in benzene and toluene. Now, something that's typically highly frowned upon because they're carcinogenic. Okay? So they're very commonly found. The name aromatic, I'm still not quite sure I believe this, because I would have figured the original fragrant oil that we would have recognized would have come from what functional group? Not aromatic. So that's where the name is coming from, the fragrant oils. There's another functional group that I would typically classify more appropriately with fragrance. Esters. The ester functional group is primarily responsible for pretty much any fruity smell or flower smell that you can name or recognize. Think of apples, pears, any kind of fruit. Almost all of those are due to an ester functional group, not the aromatic. So it seems kind of odd as far as the nomenclature goes. Okay. Quite common, so they go through and they've provided a couple different drugs that have aromatic rings in them. They do have some kind of interesting features. That ring, what's the hybridization across all of the carbon atoms within that ring? They're all sp2 carbons, which means what's the bond angle between each of those? 120 for an sp2. If we were to draw this out, including wedges and dashes, would it be necessary to show wedges and dashes? What geometry do we get out of something that's sp2 hybridized, or 120 degrees? Trigonal, planar. The benzene ring is entirely planar. There's no need for wedges and dashes, okay, which is kind of cool. What does that mean? We can now hope to not have to worry about for the rest of this section of material. Stereochemistry is now going to disappear. We don't have to worry about it as much because we're in a planar structure. We don't have that stereochemistry option. No wedges and dashes. Okay? So that can make things a lot nicer. That might be one of the reasons why I like aromatic structures a little bit more as well. Okay? I don't know why they put this together, but apparently coal contains a bunch of aromatic rings that are fused together and then joined by different other pieces. Graphite is aromatic sheets. Okay, a whole bunch of aromatic rings attached to each other, and then those sheets can slip and slide over the top of each other, which is why graphite works actually as a lubricant, because of that kind of system, that slipperiness associated with it. Nomenclature. So in most cases, at least in the simple ones, we're going to look at that benzene ring or our aromatic ring as our primary substituent. Okay, because it is the primary substituent, instead of going through and referring to it based on how we might process it, how many carbons are in that ring? 6 carbons, which would mean what Greek prefix? Hex. Okay. Are we an alkane or an alkene? We're looking at an alkene. How many alkenes do we have? 3. So we could be looking at hextriene. Where are each of those double bonds? One starts at position 1, the next one 3, 5. So instead of referring to benzene as benzene, we could look at it as 1,3-hextriene. Okay? It gets a bit tedious to say, so we shifted that into benzene. And this is a nice, more condensed fashion. So when we're looking at that ring, that's our typical reference is benzene. In most circumstances that you're going to deal with as far as nomenclature goes, benzene is going to be your primary substituent or your parent chain, and you'll name the rest of the groups that are attached to it as substituents on it. Okay, so in the first case, we're looking at our benzene ring as our primary chain with a chlorine attached to it. And they went through and highlighted that in red, so I'll go through and underline our parent chain in blue with our benzene. Chlorine is now attached, so we could go chlorobenzene. Okay, why do we not include the number of where that chlorine is located?
It's always going to be 1.
It's always going to be at position 1. Okay, so we don't have to worry about numbering it.
If you had another chlorine 2 carbons over, would it be 3 or 3?
Since you've asked, let's go ahead and just look at it. Let's draw that example out real quickly. If we have our benzene ring with our chlorine, and then you said 2 away?
Sure.
Okay. To figure out how to name this guy, it's a little bit more complex than what we're looking at here, because here it's the simple mono-substituted version, so just one piece added to it. First way to approach, we start with our parent, which is benzene. We could then look at our substituents. What do we call our substituents? How many chloros do we have? 2, so we can do it. Dichloro. We now need to specify where each of those chlorines are located. Okay, how do you want to go through and do this? Okay, first one's going to be at position 1. And we could either number, what is that, counterclockwise or clockwise? Okay, does that necessarily matter? So clockwise versus counterclockwise doesn't matter. What does matter is that we get the shortest distance between the next substituent. So in this case, we would number clockwise because when we go through and do that, that puts the next chlorine at position 3, whereas the other direction, we'd be at position 3, 4, position 5. And when we go through and put our name together, we want the smallest number for each of these. So to finalize, we could then go through and say we've got a chlorine at position 1 and a chlorine at position 3, 1,3-dichlorobenzene. Okay?
So is that considered IUPAC then?
I was going to go through and add an extra layer to this, and with that extra layer, I have no idea if it's IUPAC or common. They're probably both IUPAC. So is there another way we could refer to these positions? That's going to be the next question. Okay. Chemists are kind of notorious, particularly organic chemists are notorious for not liking numbers, because we can't count very high. Even 1, 2, 3 is a bit tedious to go through and do. So instead of saying position 1, 2, and 3, we can go through and start labeling things with a particular name associated with it. Right? So we'll pick our primary substituent, in this case our chlorine. I'm not going to draw it on that one. Let's go up to the nitrobenzene and look at the names that we could go through and do. Okay, so it stands out a little bit differently. Our nitro is now our primary position. If we added something else to this ring, we could potentially go all the way around it at each of those extra positions. Okay. Based on your understanding of NMR, if we made each of those hydrogens, how many hydrogens would show up in the NMR spectrum? How many peaks would we see?
3.
We'd see 3 sets. Why only 3 sets?
Because the opposite sides are equal.
Okay, our opposite sides are equivalent to each other. So we would get 3 independent sets. We could go through and refer to those positions based on their numbers, as we just went through and did. Okay? Or, because we don't like numbers, we can come up with a name for them. Okay? The names that we get: ortho, meta, and para. Okay? So those individual positions can be used in the name instead. Okay? It's kind of up to you as far as that nomenclature system. So you might see it labeled in that case. It's a bit odd to go through and look at our dichloro in that respect because both those substituents are chlorines. And when we go through and use the ortho, meta, para nomenclature system, we're including the nitro as part of our parent chain. Okay, and when we get to an example, which we will, we'll kind of clarify what that means. Ortho, meta, and para involve an awful lot of letters, so as much as chemists don't like numbers, we have an even bigger issue with sequences of letters. Let's take a look at our periodic table. We don't write those out as all of the individual names, right? So instead of referring to these as ortho, meta, and para, you might also see them as O, M, and Y. Just testing. That's P. Okay? So you've got those nomenclature systems potentially showing up as well. Okay? Typically, when you see the ortho, meta, and para, well, actually not typically, always, you're going to be a more complex structure. Okay? That's why we went back to the dichloro, or why we could get into that. So let's go ahead and erase all of that. With the names that we've got here, they're simple. There's only one substituent. There's no need to reference each of those extra positions according to ortho, meta, or para, because there's only one position there, which by definition is going to be position 1. We don't have to label anything beyond that. Okay? Where this is going to get a bit obnoxious as far as nomenclature goes is that you need to be able to name individual substituents. So that first one, you could probably pick off. How about the last one? Okay, our substituent is out here, right? How many carbons is that? 2, so we have our ethyl, with the YL being our substituent name, clarifying that that's our substituent. Where I would say you can kind of get in trouble is with more complex substituents. Okay, the NO2. You may or may not know this, but NO2 is typically referred to as nitro. You are responsible for knowing that it is nitro. Right? And I have no way to tell you beyond that other than it's nitro. Okay? You'll notice that nitro also does not have the characteristic symbol for our substituent. What's missing? Don't have the YL as well. Okay? So just kind of be aware of that. Nitro is definitely one of those. I think most of the others, unless you're going for a common name, are obvious. I think the nitro is the one that's the most tricky as far as piecing that together, getting a name for it. Okay? Why would nitro get its own special name? We could go based off of common, but benzene isn't necessarily common, and benzene got its own name. Why do we refer to an OH? Take a look at, sorry, now I'm getting all confused on what I'm trying to draw. When we write out this versus this, both of those OHs are OHs, right? Do we call them the same thing? No, why not? Chemistry changes. Okay? Why are we looking at NO2 as a nitro as opposed to some other kind of IUPAC association? The chemistry is drastically different due to the nitrogens and the oxygens being bound to each other. Okay? Just as a real quick test, the ROH is known as what? And the other one, I shouldn't write that out. And the other one, carboxylic acid. Okay? Where you're going to also have to watch out is some of your benzene derivatives are going to have very common or common names associated with them. I will piece through your tests to make sure that you don't need to know these. If you do need to know them, I will let you know. Okay? It's not something I would expect you to have memorized. The test or the homework may give you the name. Feel free to look it up. You don't have to have that memorized, at least currently. Okay? If I go through and look at the ACS test and they're going to throw these common names at you and you'll need to know them, then I'll tell you that, yeah, you got to double back over these and memorize these individual comparisons. Okay? I would say there's a rhyme or reason behind them, but there isn't. Okay? Or at least none that I have found recently. One for sure that you should know of that list, any ideas? Which one do you need to have memorized already? The phenol. You'll notice that I'll say phenol maybe slightly differently. At least it sounds different in my head. I say phenol and I try and accent the O with that OL. Why do I want to add that?
So it doesn't sound like a substituent group?
So it doesn't sound like phenyl with the YL as a substituent. Okay? Drastically different chemistry. Okay, so I'll try my best to enunciate that and make sure it's clear. Be aware that you should watch out for that too. Okay? The rest of those I don't think you'll need to have memorized. You might be able to piece some of them together. You might already know some, like the benzoic acid. Some of them give you information about their names, like benzoic acid probably has an carboxylic acid functional group. Benzaldehyde probably has an aldehyde. Okay? Typically they're straightforward as possible. You just kind of have to do the best you can with them. Okay? Questions about those? Okay. Benzene derivatives. So when we go through and look at the simple nomenclature system, we looked at the benzene as the parent chain. Okay, so we had chlorobenzene. So benzene was our primary group. What happens if we decide the rest of the structure is more important or has a higher priority functional group on it than the benzene ring?
Benzene becomes substituent.
Benzene now must be the substituent. Okay? If benzene's going to be a substituent, we have to be careful with the name that we're going to use. That's going to refer to our phenyl. Okay? So it's not benzyl or anything along those lines because benzyl implies that extra carbon. So when we take a look at the structure that they've got drawn first as an example, they've again already highlighted, we're looking at the phenyl as a substituent on the 1, 2, actually let's circle that, 1, 2, 3, 4, 5, 6, ran out of space, 7 carbon chain. Okay. How do you decide which is the parent chain? What's that? We'll count the carbons. Your benzene ring has 6 carbons in it. If the other part of the structure has more carbons than the benzene ring, the other part of the structure should be the parent chain. So that's why we'd go with phenylheptane in this case. The other option, what if you have a higher priority functional group? Well, what do I mean by higher priority? What's higher priority than an aromatic ring? Okay, unfortunately, again, I don't have my slides to be able to slide it in there. Remember with the nomenclature review slides that we show every so often, there's that red box. Within that red box, I organize the priority of the individual functional groups, right? Aromatics, I'm pretty sure, classify under alkenes, which means virtually everything has a higher priority functional group than your aromatic rings. Okay? So if you have a hard time trying to name whatever that extra piece is as a substituent on the ring, you're probably naming it the wrong way, and you should name the ring as a substituent on that larger piece or that other piece. Okay? So just kind of be aware of that when you go through and try and piece these things together. Yeah, since you've got it. So the slide looks something like that. I don't expect you to be able to read it from here. Okay? But that's your general slide with it. Your alkenes are at priority 7 on this list. Amines, alcohols, ketones, aldehydes, esters, and acids. So pretty much anything with a heteroatom, excluding halogens, shows up as a higher priority group. Okay. There are exceptions to that. What's our first exception that we can think of already? What group has a sequence of heteroatoms that are classified as a substituent on the benzene ring? The nitro. Our heteroatom is nitrogen and oxygen in those cases. Okay? So just kind of be aware of that. Next thing that we can look at is sometimes symbology as far as simplifying. You may have already seen this as well. You can see these aromatic rings drawn out as pHs. pH for phenyl. Okay? The other option, if we're going to get really, really lazy, and it's actually due to this slide that I actually learned this, okay, you can see sometimes that, whoops, I drew that pretty awfully. You can sometimes see the circle with the line through it. Okay, apparently that's not just a circle with a line through it. Apparently it stands for the Greek letter phi. Okay, for phenyl again, and getting that pH in there. Okay, so just kind of be aware of those different notations. We're going to look at another notation for your aromatic ring a little bit later on, once we actually discuss something about its chemistry. Okay. Our derivatives. So this is when we get in more complex structures. In some cases, we can go, oh man, I really did this on it too. You'll get some common names. So in this case, xylene is an aromatic ring with 2 methyl groups attached to it. So there's a couple different ways to approach it. We can go through and name it as xylene, which now implies those 2 methyl groups. But then the question is, where are those 2 methyl groups relative to each other? Okay? In the first case, they're right next to each other. Okay? So what we're saying is if we went through and referred to, say, this is our main piece, okay, this carbon, our next carbon over, is at what position? All sorts of fun names we can throw on this. 2 is a good option. What other things could we refer to it as? Ortho or O. So for some reason, when we're looking at xylene in particular, we could refer to it as orthoxylene, saying that those 2 methyl groups are located immediately next to each other. The other way that we could approach that name in kind of a more sensical fashion or logical fashion is look at it as a benzene with 2 methyl groups attached, just like we did the dichlorobenzene. Same general idea. What else could we do with it? And I circled it in blue as kind of a hint. What is identified in blue? It's not officially benzyl. Why is it not benzyl?
Because it's not the substituent.
There's not a substituent. Okay, so it's not benzyl. What is that group? It's one of those common name ones. Toluene. So we could name that as toluene. Do we have a substituent on that toluene? Yes. What's that substituent? Methyl. Where's that methyl located? Where's the methyl located? Position 2. For it to be toluene, our first methyl must be the one that's part of the name of toluene. Okay, so our substituent methyl is at position 2. So we could call it 2-methyl-toluene. What else could we use instead of 2? Ortho. What else could we use instead of ortho? O. Okay? So be aware that you can see numbers show up or the letters in reference to each of those individual positions. So you can apply that across to both the metaxylene and the paraxylene as well. So the ortho, meta, and para are referring to those individual positions, and that's about it. Okay? Questions about that?
Will we see the actual, like,
This is easier.
Sorry. Will we see like 2-methyl-toluene, something like that to trick us?
2-methyl-toluene is a valid name.
Okay.
Yeah.
So it is valid. It's
Yeah.
used.
Is it commonly known as that, or is it more?
It's more commonly seen as xylene. Yeah. Okay. On a test, I would probably say 2-methyl-toluene. I wouldn't give you xylene. Okay. Xylene is just, yeah. Okay. So the textbook went through and broke down the rules. Identify your parent chain, identify your substituents, all this fun stuff should be relatively review for you, so we'll just kind of skip over that. With an example here, we could go through and identify our parent chain. Nice of them to go ahead and color it in for us. Okay, so let's come up with some possible names that we could go through with this. So one approach would be to say our parent is okay. I like that approach a little bit better than what I was going to suggest. We'll go with phenol, which is highlighted in red. Why did you not call it based on this?
Alcohol's got higher priority.
The alcohol is a higher priority than the benzene ring. Okay? So we could try and put together a name with the alcohol as a substituent. Doesn't make as much sense because the alcohol has a higher priority. It makes more sense to refer to it as the phenol. All right. Next part. What are our substituents on the phenol?
Two bromines.
Our two bromines, so we get dibromo. Where are they located? 3 and 5. Okay. This brings up an interesting question with the meta. Meta typically only gives you a relationship between two groups. Right? Or I'm pretty sure only gives you the relationship between two groups. In this case, we have 3 groups on there. Pretty sure you have to call this 3,5 dibromophenol. You can't call it meta because the meta only specifies where one of those bromines go. And I don't think, but I'm not positive, I don't think you would call it meta-meta dibromophenol.
Because the bromines could be shifted over one way as well. It'd still be meta,
No.
but
Meta, as far as I'm concerned, is going to say that the relationship back to your parent chain. So if we said meta, dibromo, one of the bromines is at the meta position, the other bromine is at the other meta position to the phenol. Why would it not go on the same carbon?
Because otherwise you have too many bonds, it
Yep.
wouldn't be benzene.
Too many bonds at those carbons. Okay? Kind of makes sense? Okay. Oh, they broke it down for us. So they went through and labeled that the rest of the way out, which we've already gone through and done. So we'll go ahead and, whoops. Did I double tap on that? Yep, I did. Okay, do you guys want some examples? I'm hearing some no's. Okay, so we won't do any more examples with these. I will mention that the 3 of these compounds would probably all get named based on their common names. We're looking at benzaldehyde for that first one. The second one is toluene. The last one is anisole. Okay, don't ask me why I know that, because I have no idea why I know that. Okay, sometimes it just sticks. Next part, we'll evaluate the structure of benzene and what's going on with that. So when we look at an individual benzene ring, just as typical, we tend to imply the hydrogens, and we also specify our carbons as points instead of actually writing out each of the carbons. And we've got the double bonds alternating all the way through that. Okay? Can we draw resonance for this structure?
yes.
Okay, how do you know you can draw resonance? You have pi bonds. So we can start with one of our pi bonds and shift it over to one position. Okay, and this, as is always, I would highly recommend that you go through and approach it in this fashion. Okay, as with all resonance. What happened to the pi bond on the left-hand side? Have I shown any arrows to it? No, so what happened to it? Nothing. Okay. What happened to the other pi bond? Okay, at this point, nothing. And the pi bond that we started with has now changed positions, right? Where is it now located? Okay, on the right-hand side. Before we actually address the issue of that, what happened to our topmost carbon? Hybridization actually did not change on that carbon. Becomes positively charged. It lost that pi bond, so it is now positively charged. Okay. We could go through and evaluate hybridization. It still has 3 electron groups. And I'm sure anybody that's really picky on organic chemistry will hate me for drawing that hydrogen the way I did. But they can deal with it. Okay. We still have 3 electron groups on each of those carbons. So we could still say we're looking at hybridization of sp2. There is one big problem, though, that may not have jumped out at you if you didn't draw on the hydrogens.
Too many bonds.
That carbon now has too many bonds, which means our initial arrow drawing was wrong. We have to go back and fix it. Okay, to go back and fix, what do? Okay, we'll have to move another pi bond. Okay, and there's a couple ways we can do that. We can move that pi bond from either bond to atom or bond to bond. It's up to us. Okay, which do you guys want to prefer to do?
Bond to bond.
Okay, so if we go bond to bond, we can put it over here. So we can go back to our initial drawing. What we've done is put the pi bond over here. Any problems with that? What's the issue now? Same problem, so we've got to break that other pi bond. Let's move that pi bond up to here. What's the result?
You have a benzene ring with all the double bonds one over.
All we've done is shifted the pi bonds around, and it looks like now if we try to directly superimpose across, it doesn't seem to superimpose. Okay? We can go through and do rotations or flips as well, but what we're trying to address more importantly in this case is what's the relationship between these two structures? They're resonance structures. So when we draw out an individual benzene ring, what we're only doing is drawing one possible conformation of it. We aren't drawing all of them. Just like when we look at a carbonyl, when we draw that out in the neutral state, we aren't looking at that positive negative, even though the positive negative tells us about the chemistry. Okay? So when we're looking at benzene, depending on what we want to see, you might see it drawn with all the double bonds in there. Realize that when we go through and do a mechanism, if I start with the one on the left and end the reaction with that one on the right, I still have a benzene ring. Okay? It has still all the same chemical properties. Nothing is different about it. Okay? One extra way that we could go through and do this, let's see. I don't know if they do it on this slide. Okay, yeah, they do it on this side. So there's our new version of it. Somebody went through and said, well, if I'm going to draw these out a whole bunch, and it doesn't matter necessarily that where I put the double bonds, I'm going to come up with another way to do it. I'm going to draw with my cyclohexane with now a circle in between. What's that circle supposed to show? It's representing all of the electrons within the pi system being shared equally all the way around the ring. Okay, so that's what's going on with that circle. Why would we draw one versus the other? When benzene reacts, how do you think it reacts? What part of it is going to be the most reactive? The pi bonds. If we draw it out as, what is it, Kekulé suggests with the ring at the bottom, do we see the pi bonds? No. So depending on what we're going to try and do as far as a reaction goes or mechanisms, we may decide to include it or draw it as the ring, or we may draw it out with each of the individual double bonds so that we can see what's happening with that chemistry a little bit better. Okay? So just kind of be aware of those different representations. Next fun part is to actually address the stability of benzene. Okay? So if we go through and take a look at bromine, okay, we just addressed an aromatic ring is reactive because of the pi bonds, the double bonds. Well, 3 pi bonds, we would expect 3 possible places for it to react. We might expect that to react even faster than if we just had a single double bond. And it turns out we see the opposite result. Benzene, when mixed with bromine, typically gives no reaction. Okay, so there's got to be something else going on. Those pi bonds have to be doing something different. Okay, well, if they aren't reacting, what does that mean about the energy of the pi bonds in the aromatic ring versus a standard alkene? Has to be lower in energy. Okay? So that observation is what's changing the chemistry here, and now we have to come up with some explanation for it. Okay? So I'm not sure that I really wanted to see this, okay? But it kind of works. If we start with a cyclohexane, so fully saturated, that's going to be lowest in energy. Why would our cyclohexane be the lowest in energy of all of the structures drawn up here? No pi bonds. Why are they stable? There's no real differences in electronegativity to generate partial charges with our positive and negative. We don't have pi bonds. okay, that put electron density further away from the atoms and accessible to react. So our alkanes tend to be the lowest energy and the least likely to react. As soon as we introduce a pi bond, okay, so in the case on our far left, what happens? The energy should go up because now I've got a pi bond. That pi bond puts the electrons at a higher energy. They can now potentially react with something. What happens if we add 2 pi bonds? We would expect it to go up even more, okay, because now we're getting rid of more and more alkane structure. When we go all the way up to the aromatic ring, we would expect it to go up even more in energy. And it turns out we don't see that. Okay, and that's what this slide is attempting to show. And what they're doing is going back to something known as the heat of hydrogenation, which I will admit I have an awful time and always have to draw out a diagram like this to answer any heat of hydrogenation question. Okay? When they're referring or asking about the heat of hydrogenation, we're talking about reacting that species with hydrogen. What does hydrogen react with? Pi bonds. Okay? The heat of hydrogenation is the energy released as we go from our alkene down to our alkane. Okay? That loss of energy is your heat of hydrogenation. Okay? It takes a little bit of practice to get used to that. Like I said, I still can't do it in my head, and every single time I draw it out, I have to draw out some stupid big-ass diagram to do it. Okay? So when answering those questions, I would recommend that you go back to something like this. Draw out the individual structures and predict what would happen to their energy as we add pi bonds. Okay? So what this is saying is that when they actually looked at an aromatic ring, instead of it being 360 kilojoule loss, we lost only 208, okay, which means it had to have been lower in energy. Why would that be the case? Okay? Remember when we looked at, let's say, let's shift to this. Okay, remember we asked questions where I said which is higher in energy? Okay, feel free to say you remember and have me stop drawing anytime. Which of these is lower in energy? Same number of pi bonds, right? The bottom one was lower in energy. Why was the bottom one lower in energy?
More space to transfer electrons.
When we put that electron in, it can jump into a parallel p orbital. Well, if it jumps into that next one, it can jump into the next one and the next one. When we look at the top case, what happens? It can only go back and forth because of the node running through the middle of the structure, preventing the hopping, okay, into that other p system. Pi system. Pi system sounds fancier. When we go through and look at benzene, come on. When we look at benzene, we draw out, take a benzene structure and draw it out nice and flat with our standard drawing, right, with our cyclohexane looking thing with the double bonds in it. And we pull, say, that front carbon up and towards you, out at you. What happens is we can now see those p orbitals. All of the p orbitals in that benzene ring are parallel to each other, which means as soon as we put a single electron in there, it can now jump to every single one of those other p orbitals. What is that going to do to the energy of the p orbital, or that electron? It's going to decrease it, which means it's going to be what as far as reactivity? Less or more reactive? Less reactive. Okay? So we could go through and look at all these molecular orbital stuff and have fun with that, but ultimately all we're trying to say is that those electrons can move throughout the entire structure. The more delocalized the electrons are, the more stable they are, the less reactive. Okay? Oh, geez. More node stuff. Okay. So, stability of benzene. So does every fully conjugated cyclic structure have this stability? Okay, well, if we're asking that question, more than likely the answer would be no. Okay, so the question then becomes, well, why not? So we take a look at cyclobutadiene. We could make the same argument that we did with our benzene, and we could pull that out so that we can see it in kind of 3 dimensions. I'm going to pull it on kind of an angle here. And we could put in our p orbitals and all of those p orbitals would overlap. Why does the cyclobutadiene not give us that extra stability that we would expect with benzene? Well, any quick theories?
Angle strain?
We could jump to angle strain. That's a pretty good thought. So maybe that's why it's not more stable. So let's jump to cyclooctatriene, that thing. The stop sign one with the double bonds. Now we don't have the issue with angle strain because we've added those extra carbons. It's expanded. Would we expect that one to have the extra stability? Again, it turns out not. So it's not just an angle strain issue. There has to be something else going on. Right? What?
Size availability?
Nope, that still goes back to angle strain kind of issue. Okay? So there's some other problem happening within this. And that's what they're trying to show, is that these these two species can now react relatively readily in comparison to, say, benzene that floats around on its own relatively stable. Okay? So why is this the case? So it took a whole bunch of much smarter people than me to come up with different theories to kind of produce these different rules. Okay? So your textbook has actually simplified it to 2 rules. I think I've got 3 or 4 in how I would approach it. So an aromatic compound has to fulfill a certain number of criteria. Okay? The first one is that we need those p orbitals. Okay? That's what's dropping the energy so substantially, or partly one of the reasons why it's dropping the energy, is that the p orbitals all overlap with each other. Okay? So we have to have a fully conjugated ring with all of those p orbitals. And it's got to be a ring so that the electrons can cycle all the way around. It's not forwards and then backwards. You know how much we hate going backwards. Okay? I always walk into stuff. Okay? The next rule is Huckel's rule. Okay? And again, I don't like how this is phrased. But what he's referring to, or what they came up with, is an odd number of electron pairs is what was necessary for it to be aromatic, to exhibit this stability. Okay, well, odd number. What we're looking at is this formula. This formula, I would say, is the most important aspect of it. Looking at 4n plus 2 pi electrons. Okay, that n can be any number, okay, any whole number. One way that you could go through and do it is, instead of memorizing that formula, we could go through and look at the possibilities. What are possible sets of electrons? 2, 6, is it 10? 2, yeah, it's 10. Then it goes, what, 14? Goes up by 4s, doesn't it? That's 0, 1, 2, 3, 4, 16, 18, okay, etc. So what we're looking at as those numbers. Okay, so you could remember the formula, or remember that an aromatic compound must have that one of those possible numbers of pi electrons. Okay, which brings up a new question. How do you count pi electrons? Okay, so let's take a look at benzene. Nice of them to give you an example of one that is aromatic. How many pi electrons are in benzene?
6.
Right, what we would go through and do is look at the pi bonds. So we can color in our pi bonds. It's a different color. Each of those lines represents how many electrons?
2.
2 electrons in a pi bond. 3 pi bonds, we've got 6 pi electrons. Okay? If we go back to Huckel's rule, we said 2, 6, 10, 14, 8. Is 6 belonging to that set? Yep. Benzene matches Huckel's rule. Okay, cyclobutadiene in the stop sign one. Okay, sorry, I just can't say that. Allegedly didn't or don't have the same stability. Okay, so we could see them reacting with each other to make different structures. So we need to come up with some way to see how Huckel's rule satisfies that. So how many pi electrons are in cyclobutadiene? 2 pi bonds, we're looking at 4 pi electrons. That does not match Huckel's rule. We have to have 2, 6, 10, etc., not 4. What happens with the cyclooctatetraene? show off. I heard you. Okay. We get 8 pi electrons. Again, it does not match Huckel's rule. Okay? So Huckel was able to observe this, but he didn't have a good, or I don't think he had a good explanation for why, at least at this point. Okay? So what we need to do is then start to realize that we get different relationships. We have aromatic compounds, and we have compounds that might look aromatic, but aren't. Okay? But could we also come up with compounds that don't even look aromatic? Okay, cyclohexane, is that remotely aromatic?
No.
No, why not?
It's not a fully conjugated ring.
Doesn't have that fully conjugated ring. Okay, so why bring this up? Well, we have 3 possible results that we could be looking at here. Okay, benzene, we said was what? Aromatic. Cyclobutadiene versus cyclohexane, okay, have very different relationships. The cyclobutadiene looks like it could potentially be aromatic. Our cyclohexane doesn't have a shot in the heck for being aromatic. So we want to come up with some way that we can distinguish between those two while still bringing in some information about aromatic. If we said not aromatic, well, they're both not aromatic, but one looks aromatic. So just calling them both not aromatic doesn't go through and explain accurately enough the information or the differences between those. So what do we end up changing in this case? Our cyclohexane is non or not aromatic. And our cyclobutadienes and cyclooctagon thing are anti-aromatic. Okay? So we're going to end up having to look at individual structures and apply these 3 different classifications. Either aromatic, non-aromatic, because it can't possibly match our first definition, and then anti-aromatic. It may match our first, but it doesn't match our second definition. And we'll look at some other qualifications of the anti-aromatic in a second. Yes, sorry.
So it is the number of electron pairs, correct?
No.
Because then it gives you the total number of electrons.
Yes, no. Because you could have N be 0 and have an aromatic system.
It could just be a simple oxygen.
2 pi electrons. You can actually do it with cyclopropane. It's going to be a much smaller structure, but yes, you can pull it off with other structures.
What does the N stand for?
The N stands for a number, a whole number integer, between 0 and
So it doesn't
infinite amount.
directly correlate to
The number of pi or the
any part
pi
of it?
parent. No. Yeah. I know it's an odd thing to throw in there, but that's why I went through and did the 2, 6, 10. Those are your numbers of pi electrons. And if you stick with that, that should help you out.
Because in essence, it's just counting and making sure you have an odd number of pairs on the ring.
Yep.
Is that all?
Well,
So
so
if I
that's
have 5
the
pairs
other way you
of-
could do it. If you have 5 pairs of, then it's an odd number that would match Huckel's rule. Okay, because that's an odd.
With there being an equation, not understanding where it goes.
Yeah, the equation happens to be a derivation of the patterns that they saw. Okay, so it's up to you whether or not you want to use the equation or not. And that's coming from how they found this and looking at different pi systems and developed it. Okay. Other questions? Okay. So what's going on with another approach to this? We can look at Huckel's rule using molecular orbital theory. So this is another approach. Instead of looking at the equation, we can now start to explain the stability by going through and looking at our molecular orbitals. Okay? Most people tend to really not like that, but hey, it can be kind of fun to go through and do. If we take a look at cyclobutadiene, we end up with 4 possible orbitals when you go through and put it together. Okay, so you can arrange those orbitals, generating new nodes or no nodes in differing fashions to generate these 4 possible orbitals. So the bottom one, come on, they've actually already got shown. Okay, right? So if we draw out, I'm not sure I'm going to be able to do this neatly. Okay, with our orbitals all directly overlapping or all the same shading, right? There are no other ways that we could get all of those shaded. So there's one molecular orbital. Is it possible that we could now change the shading? Okay, so add a node, so increase the energy. What could we do? Let's see, I'll draw it underneath here. Okay, it's a valid possibility. You see the node running, okay, through that plane, right? Is there another way that we could have shaded it? As a big hint, they're drawing another line, so yeah, you could. Where's the node in this case? It's in a slightly different plane. What we've looked at is what's known as degenerate orbitals. They're the same energy. Okay? We could then go through and add yet another node, and we'd get our anti-bonding orbital where none of those overlap with each other. So we get 4 possible molecular orbitals. Okay? With those 4, we'd then go through and try and determine our pi electrons. How many pi electrons do we have with cyclobutadiene? 4. We would then go through and put in our 4 electrons. I'm going to go ahead and clear everything so we can see it a little bit cleaner. And they went through and did that. We'll start putting them in our lowest energy first, then we move up to higher energy. Why do we not pair them when we deal with our next set? Why is it not drawn with the 2 electrons in the same orbital? You fill all orbitals with equal energy first, then you go back and refill. Okay? So what happened at the end of this result, or the end of this, is that we end up with 2 electrons that are unpaired. I'll go through and erase everything again. We get those unpaired electrons. Well, electrons do want to be paired. Okay, that is their natural state. Unfortunately, they aren't paired in this case, which makes it a higher energy system. Okay, what happens? Please be right. Come on. Yep. Really? No benzene. No really? Okay, sorry. I'm giving someone a headache for watching this. So let's take a look at what benzene does. Okay, if we went through and drew out benzene, what we'd end up seeing is something along these lines. Okay, and I'll leave you again to determine those molecular orbitals. Here's our energy. And we have how many electrons in benzene?
6.
6. We fill 1, 2, 3, 4, 5, 6. Interesting. What's the result? All our electrons are paired. We don't have that unpairing. So when we look at benzene, we have a more stable conformation because all of our electrons end up pairing up, okay, as opposed to leaving them in unpaired orbitals. Okay? That's one of the things that contributes to that stability. If we now went and looked at the one I can't say, the one that shall not be named, we could go through and again look at similar orbital situations. We'd have our lowest energy. We'd end up with degenerate orbitals, and we'd end up with multiple degenerate systems. With that compound, we have 8 pi electrons, so we go through and attempt to fill that one. And again, we notice that we end up with 2 orbitals with only a single electron in them. Okay. Our pattern is starting to come out of this. When we look at our molecular orbital theory, we can see that we get these unpaired electrons. That unpaired system of electrons is not a stable conformation. Okay? And we don't see that aromatic stabilization. So we end up referring to it as anti-aromatic. Okay? Questions about that?
Do we need to know this before they see it? Like,
You need to be able to figure out aromatic versus anti-aromatic versus non-aromatic, yes. Knowing how to deal with all the orbitals, not as big of a deal. Okay? As complicated as that may have seemed, it actually isn't too bad. There is kind of a shortcut to it, which I don't think was the next slide, but as I clicked through it. Okay, we'll come back to that in a second. This compound shows up as anti-aromatic. Okay? Anti-aromatic is a bad thing. So stupid structure does not want to be in that situation where it could even be considered anti-aromatic. So to be anti-aromatic, we have to have all of the p orbitals overlapping each other and have that even number of pi electrons. Okay? So what the structure goes ahead and does is, instead of being planar, the actual structure puckers. Now those p orbitals are not all in the same plane. Now it's not anti-aromatic. It's not even a potential for being aromatic. It becomes non-aromatic. Okay? So structures, if they can adjust to get away from that anti-aromatic system, will. So for instance, cyclobutadiene, could it adjust its structure to avoid being anti-aromatic? Not really. There's a little bit of wiggle room in those bonds, but it's a very, very small amount. Okay? So if you tried to build that, you're not going to be able to bend those carbons off axis of each other. They're all going to be in the same plane. Okay? So, lesson for today, nomenclature for your aromatic rings and being able to determine aromatic, anti-aromatic, and non-aromatic. Okay? On Monday, we'll go through and look at a couple more examples for the stability. So identifying compounds as aromatic and anti-aromatic, and also looking at, okay, when I was drawing out all those orbitals and saying the different energy levels, you can come back to something known as frost circles. So you can follow these individual steps, and you can draw those molecular orbital energies without actually having to predict all of the overlaps between the p orbitals. Okay? It's kind of a neat little trick associated with it, not that big of a deal. You can figure everything out without having to do that, okay, based on the rules already discovered for you. Okay, so sorry we're running a little bit late, but I'll go ahead and stop there.